Let us now consider another example in which the Laplace transform technique is applied to a circuit containing sinusoidal sources. So, you have a sinusoidal voltage source of 10 sin omega t as the voltage, and the switch is closed at t equals 0. Let there be two elements in the circuit R and L, and you are interested in finding the current in the circuit for t greater than or equal to 0, and it is given that I 0 is rho. Because of some previous switchings, previous arrangement, the current in the inductor is I 0 at the time of switching. So, we make the transform diagram for this. So, the voltage source has a transform 10 omega over s squared plus omega squared. That is the Laplace transform of 10 sin omega t. And you have a resistance R, that is the generalized impedance of this. As far as the inductor is concerned, you have a generalized impedance Ls, and in addition you have a voltage source representing the initial current in the inductor, which is rho times L. The voltage of that voltage source is rho times L rho. So, that is what we are having. So, that completes the transform diagram, and in this we are interested in finding out the current IFS. So, if you write this, after all this is a simple single loop circuit, therefore, IFS can be written as 10 omega over s squared plus omega squared plus L rho, that is the total driving voltage in that loop, divided by Ls R, that is the total impedance in the circuit. Now, this can be written as, after all you have to make the partial fraction expansion for this. So, I can write this as, first of all, L rho over Ls plus rho, that is straightforward, therefore, I get rho over s plus r by L, that comes from this, plus in addition I have 10 omega over s squared plus omega squared, the first term, the ratio of the first two terms. I will write s plus r by L and divide this by L. So, 10 omega over L divided by s squared plus omega squared times s plus r by L. So, if you make the partial fraction expansion of this, you will get rho over s plus r by L as before for the first term, and for the second term you have s plus r by L, one term, and that will turn out to be 10 omega L divided by r squared plus omega squared L squared. You can carry this out. I do not spend time in working out the details, but one can easily arrive at these values. And you have, for the s squared plus omega squared term, 10 omega r over r squared plus omega squared L squared divided by s squared plus omega squared minus 10 omega L divided by r squared plus omega squared L squared times s over s squared plus omega squared. Actually, when you have s squared plus omega squared in the denominator, you have as plus b times in the numerator. I split this up into two portions, so that this can be recognized to be the Laplace transform of a sine function, this case recognized to be the Laplace transform of a cosine function. So, I f t is, for the first time is concerned, rho e to the power of minus r t over L, rho e to the power of minus r t by L, that is the Laplace transform of this. As far as this is concerned, you have 10 r by r squared plus, right, let me say 10 by r squared plus omega squared L squared that is a common factor right through. So, I will keep that separately. 10 by r square. You have omega over s square plus omega squared gives you sin omega t. Therefore, you have r sin omega t. Here again 10 over r squared plus omega squared L squared has been taken out. S by s squared plus omega squared will yield me cos omega t. Therefore, I have minus omega L cos omega t plus here 10 by r squared plus omega squared L squared is taken out as a common factor. Therefore, plus omega L times e to the power of minus r t by L and of course u of t. So, this is your all this is multiplied by u of t. U of t. You notice that at t equals 0, this is 0. This cancels out with this because cos omega t and e to the power of minus r t by L are both equal to 1. This is 0. Therefore, this term is 0 and this is equal to 1 and the initial value of the current I t is rho, which is what we know. Now, in this you observe that this term and this term can be combined if you wish. It is a decaying transient minus r t by L. Therefore, this term and this term together are the transient terms. They decay with time. Actually, both of them can be combined. Whereas these two terms are the steady state terms. You are driving this particular circuit with a sinusoidal forcing function. Therefore, there is a steady state solution and this is what we are having. You can show this steady state term to be 10 by root of r squared plus omega squared L squared, that is the impedance of the circuit, sin omega t minus theta, where tan theta equals omega L over r. So, this is the steady state solution. You have here an AC circuit in which you have a driving force 10 sin omega t and you have a r and L in the circuit. Therefore, the impedance is square root of r squared plus omega squared L squared and the power factor angle equals tan inverse of omega L over r. So, that is the steady state solution. You combine these two and you can show very easily that the sum of these two is indeed this. The transient part of the solution equals rho plus 10 omega L over r squared plus omega squared L squared e to the power of minus r t over L. That is the transient part of the solution. Rho e to the power of minus r t by L plus 10 by r squared plus omega squared L squared times omega L e to the power of minus r t by L. This is the transient solution. So, in this we can see that once we have a solution, we can identify the terms which correspond to the steady state behavior of the current and what are the terms which correspond to the transient portion of the response. So, both these are simultaneously brought out in the final solution. You can combine these terms and show it to be so. And of course, once you have the total solution that is valid only for t greater than or equal to 0, therefore, u of t will always be there to specify that I of t, that expression whatever we have, is valid only for t greater than or equal to 0. Let us work out one more example. Let us now consider this example which we had earlier discussed in the context of the classical method of differential equation approach to the solution of transients. We have a setup here in which the two inductors, the two inductors were originally carrying different currents, but once the switch is opened, both of them are perforce required to carry the same current. Therefore, this is a case of discontinuous inductor currents in the transition from t equals 0 minus to 0 plus. In the case of differential equation approach, we have calculated the t equals 0 plus conditions separately. Now, let us use the Laplace transform method and show that once you substitute t equals 0 minus conditions, 0 plus conditions almost immediately follow in the normal routine. You do not have to make separate calculations. So, let us use 0 minus conditions and solve for this circuit. You recall that the current was originally 3 amperes in the, when the switch was closed, the current in the IL1 is IL1 0 minus is 3 amperes and IL2 0 minus was 0 amperes. But once the switch is opened, IL1 0 plus and IL2 0 plus are going to be the same, and we would like to know what this value is. And we use the constant flux linkage theorem or some similar effect to find out the current, the new current in the inductors. Let us use Laplace transform techniques here. So, let us draw the transform diagram for this. You have 12 by S is the transform of the voltage source. You have 4 2S, and as far as the inductor is concerned, we use the I 0 minus values. 0 minus values 3 amperes. So, 3 times 2 6. L1 IL1 0 minus, that is 6, and down here you have inductance of value S, impedance S, and the initial current is 0, T equals 0 minus, therefore, you may as well do not have that, and you are having 4 ohms. So, what is the current here? This is a very simple circuit. So, I of S will be 12 by S plus 6 divided by 3S plus 8. That is what you are having. So, that this will be 2S plus 4. You simplify this, you get 2S plus 4 times S plus 8 by 3. S plus 8 by 3. Now, we can make the partial fraction expansion, find out the I of t, but before that let us find the initial value of the current. I0 plus equals limit as S tends to infinity of S times I of S. So, when you multiply this by S and take the limit as S tends to infinity, that becomes 2S squared by S squared, therefore, this is 2. That means this current from 3 amperes has jumped to 2 amperes at t equals 0 plus, and something else it goes like this. So, automatically you find out the I0 plus. So, if you want to find IT separately, you make the partial fraction expansion, this becomes 3 by 2S plus half of S plus 8 by 3. So, you get I of t in the loop as 3 by 2 plus half of e to the power of minus 8t upon 3 u of t. So, that current was originally 3 amperes in IL1, jumped to 2 amperes, and then finally it decays to 3 by 2 amperes. Now, what about the inductor voltage? Suppose I want to find out the inductor voltage VL1 of S. When you want to find VL1 of S, now that we have got I of S, 2S times I of S plus, that is the drop here, minus 6. So, when you want to find the inductor voltage, you must take the voltage between these two terminals, not across this inductor alone, this portion only. You must take the initial source, initial current source also into account, because these are now the terminals of this inductor in this circuit. This inductor has been replaced by not only an inductive impedance, but also the initial current source. So, when you want to find out VL1 of S, if this is VL1 of t, the corresponding Laplace transform is the voltage in the transform diagram existing between these two terminals. You should not make the mistake of computing only this portion. So, 2S times I of S minus 6, that is VL1 of S, and you can show that this will be minus 2 minus 8 by 3 e to the power minus 8 by 3 divided by S plus 8 by 3, which means VL1 of t is minus 2 delta. I will write this separately here. VL1 of t is minus 2 delta t minus 8 by 3 e to the power of minus 8t by 3. And likewise, if you calculate VL2t, that is the voltage across this between these 2 points, VL2t likewise if you calculate, you will get the result 2 delta t minus 4 upon 3 e to the power of minus 8t upon 3. So, since both the currents have jumped from t equals 0 minus to 0 plus values, you no doubt there will be impulse functions, but taking the L1 and L2 put together, the impulse functions cancel each other out. That means even though inductors have impulse voltages in them, in the local loop the impulses get cancelled. Therefore, all the other voltages are finite, and therefore the total Kirchhoff's voltage law is still satisfied, because the impulse voltage generated here is cancelled by the impulse voltage generated here, because this will be now VL2 of S, this is VL1 of S between these 2 points, and the sum of these turns out to be 0. So, we have worked out a number of examples illustrating the Laplace transform technique. As I mentioned, once we have the transform diagram, we can use the whole range of network analysis techniques that is available to us in the context of DC circuits or AC circuits. We can use the node analysis, the loop current method of analysis, superposition, the various network theorems we can apply. All these follow in a straightforward routine fashion. Later on we will return to a discussion of network theorems at some point, and then we can pick up this thread at that time. But at this time, from what we have seen, let us now see what are the advantages of the Laplace transform domain in the transient analysis of electrical networks. We find there are a number of advantages compared with the classical differential equation approach. First, when you have functions of time which are discontinuous or which have discontinuous derivatives, like your step function or ramp function, then the Laplace transforms of these time functions turns out can be simple expressions, whereas if you look at the classical differential equation, suppose you have the function is described by different analytical expressions in different regions of time. So, you have to find the solution for one interval of time, find the final solution, and put this up as the initial condition for the next interval, and so on and so forth. That becomes quite complicated, whereas in the transform domain, for the entire range of time you have one single simple expression for the in the Laplace transform domain. Secondly, we observe that we do not have to involve ourselves with calculus operations, no integration, no differentiation. All the equations describing the behavior of the system are put in purely algebraic form, algebraic equations are involved. So, calculus is converted into a kind of algebra, because differentiation corresponds to multiplication by S, integration corresponds to division by S. So, calculus is converted to algebra. A third feature is that you get the total solution, the transient part of the solution and the steady state part of the solution both together in one unit, whereas in the classical differential equation you have the particular integral solution, the complementary function. So, they are found separately and you combine them, but here you do not have to do that. You find out the total solution in one step, but once you have got the total solution, you can identify the steady state part and the transient part in the final solution using common reasoning, which is, and these terms will become evident if you see what are the terms which correspond come from the forcing function and what are the terms which come from the system itself. This will be made more clear when we discuss the system function and its ramifications later on. But the main advantage of the Laplace transform technique is that the initial conditions pertaining to the system are plugged into the solution, into the equations at the very beginning itself. Therefore, you do not have to evaluate separately the arbitrary constants that you have to do in the case of differential equations. And this is very important, because if the order of the system, the number of reactive elements becomes large, suppose there are 4 or 5 reactive elements and you have a 4th order differential equation, then you need to know 4 initial conditions, not only the initial value, but the values of the first 3 derivatives. And this becomes quite complicated because they are not evident, they are not given with the problem, and you have to calculate this. You have to find out the initial derivative, the second derivative, the third derivative through separate manipulations. All that is unnecessary as far as the Laplace transform technique is concerned. All the initial conditions pertinent to the reactive elements are used in the transform diagram or equivalently in the differential equation. You substitute them and you get the solution. So, separate evaluation of arbitrary constants is not necessary at all in the transform approach. And in this context, it is also seen that you do not have to find out the 0 plus conditions separately from 0 minus conditions. If you have 0 minus conditions, you straight away plug them in. You use 0 minus conditions, and the solution that you get is one that starts from 0 minus, automatically it will proceed. And if in fact, if you are interested in finding out 0 plus conditions, you can use the initial value theorem, the final expression, and find out what those 0 plus conditions are. So, all these are the advantages of the transform approach to the solution of transients in networks. To summarize once again, because this is a very important aspect, let me recapitulate the various advantages that we have mentioned. First of all, functions which are discontinuous and which have discontinuous derivatives are easily handled in the transform domain, because you get one single expression valid for all time. Secondly, we find that calculus is converted into algebra, so the manipulations are that much easier. Thirdly, we find the transient and steady state solution come together in one package, but you can separate them at the final solution into the two separate components if you so wish. And most important of all is the fact that the initial conditions are used in the problem to start with. The data regarding initial conditions is fed into the problem in the very beginning itself. So, separate evaluation of arbitrary constants is avoided. This is a troublesome feature as far as the classical differential equation solution is concerned. After having said all this, you must also be fair to the fundamental approach of differential equations. What is it that differential equations can do which Laplace transform perhaps cannot do? See, the differential equation solution is a very fundamental solution, fundamental approach. Suppose you have given some data, not the initial conditions at t equals 0, but you specify some conditions and the response, initial value equals so much at t equals 0, the derivative is equal to so much at t equals 1 second, the second derivative is so much at t equals 2 seconds. Suppose the data which regarding the arbitrary constants are specified in a different way, not all at t equals 0, then the Laplace transform domain is not very convenient to handle such type of data. If all the initial conditions at t equals 0 are given, then it is nice, but if it is not so, then the differential equation is much more amenable to giving us the proper solution and it certainly is a more fundamental approach. So, one will also have to keep in mind, one should also know how to handle transient problems using the classical differential equation approach. Even though Laplace transform has a lot of advantages and we for the most part resort to Laplace transforms, one should not completely ignore or forget the differential equation approach to the solution of the transient problems. Particularly in very simple cases, you can write down the differential equation solution by mere inspection. You do not have to transform those equations every time. So, it is a powerful technique, no doubt, but in very simple cases, the straightforward application of differential equations will fetch you the result quickly and also with a little bit of insight into the working of the problem. So, we have covered in these last two lectures the application of Laplace transforms to the transients in networks. Now, in the next lecture, we will take up the question of how to use Laplace transform technique to general analysis of a system. We go back to the system function that we already talked about in our preliminary set of lectures and see how you connect it up with the Laplace transform technique. This will be the topic in the next lecture.